Hmm. Hello? I. Sorry everyone for the delay. I had some network issues here. So, hello everyone and good evening. I'm Devika Muraleedharan, second year EC from MES College of Engineering. I'm actually the Joint Secretary of SPS of our college. So, you may already know my topic, power electronic switching devices and power circuits. So, this will probably be a half-hour session. I have already delayed it for a half hour due to my network issues. So, these are my main topics. So, what is power electronics and why should we care about that? So, that's what the main thing we are discussing right now. Sorry for the, yeah, I think now it's visible. So, why we are caring for that? So, in our 21st century, we basically rely completely on electronics. So, let it be our smartphones or our TVs, or probably every one of us would probably use a mail ID nowadays. This would be better. Yeah, every one of us probably use mail ID for our daily life, or probably once a week we of course mail to someone. And there was a completely different life for us. Like not for us, but our fathers, grandfathers, anyone. We don't even see nowadays a typewriter, or most of us don't even have a landline phone in our home. We only use it for probably our network connections, I guess. Our grandparents or anyone would still rely on it. And we even had different old type of car which only the aristocrats in our society used to have. So there is where the electronics come to action. We completely need a power to use the electronics. So, what is power electronics? It is an application of solid state electronics. It is used for the control and conversion of electric power as it is visible from the slide. In other words, we can say that it is a study of switching electronic circuits in order to convert and control the current flow in electric every day. Or basically, as I've said before, it is used for the control and conversion. So, of course, it involves a system used in the control and conversion. This basically focus more on the electric power. So, power electronics is an application of solid state electronic used for the control and conversion, and which focus more on the electric power. So now let's come to the main topic, power electronic switching devices. What is a power electronic switching devices? It is basically the converting of electric power from one form to another. It's the technology used behind this. And it is capable of handling high voltage and current operations at high frequency. A power electronic device is basically selected on the rating of handling of power. So, as I've said before, power electronics is focused more on the utilization. So, of course, the devices used should also have a high rating of handling of power. Next, it is used, development of control of output parameters such as voltage, current and frequency. Of course, the switching devices focus more on the output rather than the input because it is used for completing of a circuit. Electronic switches should be able to low and continuous the surge of power. That's what I've said before. It is used for the continuation of a circuit. In the picture, I think it's visible. There is a control unit and a supply power. Control unit is basically used for the controlling, and the power is basically what, in simple words, we can say a battery. This is basically the galvanic isolation. And next, the GI1 and GI2 which is written are basically the devices. It could be an IGBT, a BJT or a MOSFET, etc. This is the device used for the power electronic switches. And next comes, it is transferred to a drive. Drive is basically used for the controlling of voltages, etc. And it is connected to a power semiconductor, and thus the circuit goes on. This is basically what is happening in a power electronic switching devices. So, power switches in power system. Switching operation in a power system is very common. Of course, every day we use what? 10 and 20 types of switches in our home. Even if we get up in the morning, come out of room, we probably most of us close our switches, like turn off our lights or fan. Of course, we use switches every day. So it must not be jeopardize the system's reliability and safety. Yeah, it's the main thing used in the safety. It's basically taking into or out of a service of some sections of the system, certain loads or consumers. So we know why a switch is being used. It's used to give the current in or out of the system. So the examples are switching of shunt capacitor banks or shunt reactor, de-energizing of overhead lines, transformers, and so on. These are some of the examples used in the switching. And the next one would be the transfer of flow of energy from one circuit to another. Such operations occur when the load current needed to be transferred without interruption. So basically the switches are used in two purposes. The first one would be taking in and out of, taking the current into or out of system. That is basically breaking the circuit. Like what we do in our homes usually. When we put on the switch, the current goes. That if we are on the light, light's on. And if you off the switch, the light will be off. And another one would be turning the current to a different direction. Like if we want the current to go to the left path, but now the circuit is in the right, we can change the direction. So that are the basic two uses of a power switch. And it is also for the reliability and safety of any power system. So that's basically the power switch's application in a power system. Now let's go to the classification of a power switch. We here is classifying the power switch on the concept of an ideal switch. Everything has an ideal and a practical thing. So now here we are classifying it on the concept of an ideal switch. So the power switch is divided into three: control switch, semi-controlled switch, and a uncontrolled switch. So uncontrolled switch, we basically can understand it from the name itself. It cannot be controlled by us manually. That is, it does not have a control terminal. The state determined by the external, it can only be controlled by the external voltage or current condition. That is, we cannot control it, but an external current or a voltage conditions control this uncontrolled switches. The main example would be a diode. Next one would be a semi-controlled switch. So a semi-controlled switch, very visible from its name itself, it has very limited control over the switch. That is, we can turn on a switch but cannot off it manually. We need an auxiliary circuit to turn off the semi-controlled switch. The examples would be SCR, GTO, and an MCT, which we will discuss in our further slides. And the last classification is a controlled switch. That is a basic type of switch. It can be on and off via control terminals. It have a control terminals, so we can on it or and off it manually. The examples, the main examples would be a BJT, MOSFET, IGBT, etc. So now let's go to a little more detail. Uncontrolled switch. The main example, as I've discussed before, is the diode. A power diode and a normal diode is very different. Its applications are different. Also, it's visibly different. We can see it in the picture itself. Usual diodes would be smaller and have less voltage rating, but here it has more voltage rating. It is more bigger, and it is also a rectifier. We know that. Probably most of us engineering students know what a diode is and how it works. It has two terminals, anode and cathode. Anode is the positive and cathode is the negative one. In the ideal case, the current flow from anode to cathode, and we take the voltage positive when the flow is from anode to cathode. We all know that probably. And there are again different types of anode, but it's not for today. So we need a different session to take that. There are a lot of types. So the next classification would be a semi-controlled switch. And the first and the main example would be a silicon controlled rectifier, also called as an SER. It is a 3-terminal semiconductor switching device. As we can see in the picture, it has an anode, cathode and a gate. This is the most important circuit element after a diode. Also, it is helping in the converting of an AC to DC rectifier. We know that. It also performs functions such as rectification, inversion, regulation of power flow, etc. Regulation of power flow. That's why we're using it as a switch. Rectification. Okay, we know that. It is a unidirectional power switch. That is, it only allows a single direction. So inversion also. And it is extensively used. As I've said before, it is one of the important circuit element after diodes. So of course, it would be extensively used, and it acts as a true electronic switches. So basically, a silicon controlled rectifier is a combination of a rectifier or a PN rectifier, or PN or NP, whatever, and a transistor, a PNP or NPN. So it's a combination of both rectifier and transistor. So the next one would be a gate turn-off thyristor, a GTO. This regains the supreme in power electronics. One of the important thing in a power electronics is a GTO. This is thyristor. A single thyristor had many disadvantages, and one of the important being it being a semi-controlled device, and this addressed that problem of thyristor. So is a current control minority carrier. And this also is a 3-terminal device, and it has an anode, cathode and a gate. And this turn off when negative current is sent through the gate. So when a negative current is sent through the gate, this causes a reversal of gate current. A relative high gate current is needed to turn off this device. And also this behave like a thyristor with very low on stage voltage drop. And so the next one would be MOS or MOS controlled thyristor, or MCT. MCT is considered to be the latest, or MOSFET is used for turning off and on the MCT. There is 2 MOSFET used for the oning and offing of an MCT. This is used for the switching applications. Like the previous one, there is 2 MOSFET used. Like it is built into a gate structure. So one is used for the oning and another one is used for the offing. So this is used in the switching purpose. Of course, we know that. That's why we are discussing in the slides. And the next one would be it has a characteristic of high frequency, high power, and low conduction drop. This also is a 3-terminal device, anode, cathode and a gate. There is an NCT and PMCT, that is being negative and positive. And the last one would be the gate signals are applied with respect to the anode being the reference one. We are giving gate signals with respect to anode and not a cathode, point to be noted. Also, there are thousands of basic units connected in parallel, just like a PMOSFET in the MOS. And this also helps in obtaining a high current carrying capacity for the device. So that's all about MCT. The next one, or the third type and the final type of classification, is control switching device. And the first one would be a BJT used as a switch. Probably most of us know what a BJT is. This also is a 3-terminal device, being the collector, emitter and base. It also has 3 regions: active, cutoff and saturation. 2 regions it acts as a switch, and the third one it acts as a linear amplifier. Active and cutoff it acts as a switch, and saturation it is a linear amplifier. And probably the device is off in the region where base current is 0, and on in the region where collector emitter voltage is less than the collector emitter saturation voltage. Or in simple words, we can say that when the collector current is greater than 0 and voltage of the collector emitter is equal to 0, it's in an on stage. If we draw a graph by taking collector emitter voltage in the x-axis and the collector current in y-axis. This would probably be the y-axis. On stage would be the y-axis, and the off stage is collector current equal to 0 and collector emitter voltage is greater than 0. That would be the y-axis. So if we take a graph, if we make a graph taking collector current in y-axis and voltage in the x-axis, the y-axis represents the on stage and the x-axis represents the off stage. So also BJT is allows unidirectional current and voltage device. So that's all about BJT. Next one would be one of the most commonly used, MOSFET, that is metal oxide semiconductor field effect transistor. This is also a 3-terminal device, being the drain, source and a gate. So the control terminals resembles a gate and the power terminals are the drain and the source. This is basically controlled by the voltage in the gate source region. This is a voltage control device. This also, as we discussed in the BJT, has 2 regions where it acts as a switch, which is the cutoff and saturation obviously, and the third one, the cutoff and active, and the third one is the amplifier, that is the third stage is the amplifier. Here the voltage in the gate source region is actually the supply voltage. We'll discuss this working in the next slides. So let's go to the next or the last type of switch used, which is the most commonly used switch, IGBT. IGBT is also a 3-terminal device, being gate, collector or drain, or emitter or source. This has a double mechanism device. This is also known as a double mechanism device due to its double mechanism obviously. And it combines the fast switching of a MOSFET and the low power conduction loss of a BJT. This is this is contributing to both of the applications of MOSFET and BJT together, making an IGBT. The power terminals is a gate. The control terminal resembles a gate, and the power terminal, the collector and the emitter. This also blocks bidirectional voltage and it conducts unidirectional current. Now let's go to the working of a MOSFET or a metal oxide semiconductor field effect transistor. In the off stage, as I've discussed before in the BJT, this is a somewhat a similar graph of the BJT also. In the off stage, the V gate source is less than the V threshold. In the graph, we can see an area written as off, which is the area below VGS equal to 0. It's written as off because there, in that particular area, that is the area below the first line, here the VGS is less than V threshold. V threshold being the threshold voltage of a MOSFET. It's less than V threshold. That's why it's off. And as the VGS, that is V gate source, voltage of the gate source, increases the threshold, the MOSFET starts conducting and on stage act as a resistance determined by the slope of the line. This is a practical application, okay. In ideal case, as I have discussed in the BJT, the y-axis, the on stage the drain source would be 0 and the ID, that is a drain current, would be greater than 0. That is, it would be in the y-axis. The ID greater than 0 and VDS equal to 0 would be the y-axis. That's the off stage. And on stage. And in off stage, VDS would be positive and ID equal to 0, that being the x-axis. So in on stage represents the y-axis and off stage represents the x-axis. So that's basically a simple working of a MOSFET or a metal oxide semiconductor field effect transistor. Next would be the application of a MOSFET. MOSFET is used for lower power applications, accomplishing and its purpose. This is one to be noted as we are discussing IGBT later. I'll talk about that. This is used for low power for accomplishing. And next would be the power dissipation of its term of loss is very little. Very little power is used in the dissipation. Next would be, it's a major component in modern computers, electronic device like a cell phone, digital watches, small robotic toys, calculators, etc. So this is being used in our daily life things like computer phone, what we use daily. Because it has a low power, it uses low power in its accomplishing of purpose. I hope everything is clear. And now let's go to the last type of switch which I am going to describe, and it's the IGBT. It's insulated gate bipolar transistor. So without discussing all these lines written, I'll just directly go to the figure. The VCC in the right end, the VCC we can consider it as a battery, and the RD or the load resistance would be just a bulb or a LED light connected. Just think the collector and the emitter is the where the switch had been, like where the resistor is now, sorry, the transistor is now. Let's take that away and connect a switch there. If I had short the collector and the emitter, the current would be passing and the circuit would be closed and the light would have been blinked. So in that place where the switch had been, we are connecting an IGBT here. So the VG or the voltage given in the left tip, VG is a high voltage and RS can be manually changed. When RS can be manually changed, the voltage in the RG, that is the gate emitter area, the voltage there would also be changing. As I have discussed before about the V threshold or the threshold voltage of the transistor, if the VG, that is the voltage in that gate emitter region, increases the voltage of the threshold, as we are manually changing the RS, if it increases above the threshold voltage, the transistor starts conducting and the current starts to flow. I hope it's clear. I'll tell once more. The VG is a very high voltage and RS can be manually changed, thus changing the voltage VG which is reaching the RG area. So the voltage there will be changing according to how we change the RS. So if the VG which is being reached in the RGE, that is which is changing now to the voltage in the gate emitter region, increases the V threshold, it starts conducting. So what we have written here is when gate terminal is positive with respect to the emitter and the gate emitter voltage more than the threshold voltage of IGBT, an N channel is formed in the P region causing as in a power MOSFET. So that's what I've said. If the gate terminal voltage is increasing the threshold voltage, it starts conducting. Now let's see the graph. It is similar to the MOSFET or the metal oxide semiconductor field effect transistors graph. Here also there is the off region mentioned, which is where the VGS is less than the threshold. There it will not conduct, and when the VGS starts gradually increasing and it increases the V threshold, it's when it starts conducting, and that's the graph lines formed there. So that's basically the working of an IGBT and the applications for IGBT. IGBT is used in high power applications such as applied motor drives, electric vehicle motor drives, power factor correction converters, your uninterruptible power supplies, solar inverters, high frequency welders, inductive heating cookers. So I've said in the MOSFET it uses very low power, and here it is used for high power applications like motor drivers, electric vehicles, solar inverters, high frequency welders, etc. Here it uses high power and MOSFET uses low power. And now let's compare a MOSFET and an IGBT. An IGBT is basically an insulated gate bipolar transistor, whereas the MOSFET is a metal oxide semiconductor field effect transistor. IGBT is a three terminal power semiconductor device which is a cross between BJT and a MOSFET, as I've said before while I was explaining IGBT. And MOSFET is basically a field effect transistor used for switching and amplifying AC and DC signals. Okay, now IGBT is a MOSFET and a BJT both integrated to a single piece of silicon. And MOSFET is a special type of FET which determines the electric conductivity by the applied voltage. It controls electrical conductivity. IGBT is extremely tolerant to electrostatic discharge and overload, as why it's being used for the high power devices, and MOSFET on the other end is vulnerable to as the high impedance technology wouldn't allow voltage dissipation. Of course, that's why it is being used for the low power devices. IGBT is a three-terminal device, as I've said before. It has an emitter, collector, gate, and the MOSFET has a gate, source, and a drain. IGBT uses minimum to ultra-high power applications such as SMPS and a VFTS. And MOSFET, on the other hand, is used for switching and amplifying weak electronic signals in electrical devices like a calculator, toys, which we have discussed in both its applications. So now let's just summarize what all we discussed before. I'm not sure if it's visible, but in the x-axis it's the current, y-axis is the voltage, and z-axis is the frequency. So now let's take the thyristor, which is at that end, and it uses a frequency of 100 Hz, just 100 Hz. And it is but using the most current, which is 22 kiloampere, and most voltage, which is about 7 kilovolt or more than that. So this uses more current, more voltage, but the least amount of frequency. Next one would be a GTO. GTO is the second most using current and voltage. It uses around 2 kiloampere of current, 6 kilovolt of voltage, and 2 so 1 kilohertz of frequency. Now IGBT. IGBT uses a little more frequency, like around 10 kilohertz. It uses average of current like 1 kiloampere and 3 kilovolts of voltage. And the last one, MOSFET, it uses very low current, that is 100 ampere, 1 kilovolt, and the most frequency, which is 1 megahertz. So that's basically what the switching devices is. So now let's conclude what we had all discussed here. Power electronics is assuring a no kind of industrial revolution because of its important role in the energy conservation, renewable energy source, bulk utility energy source, and electric and hybrid vehicle. In addition to its traditional role in industrial automation and high efficiency energy system. Basically, the first thyristor appeared in the 1957, the first BJT in 1960s, MOSFET in the late 70s, and IGBT in 90s. So, we basically want everything in a compact way. Of course, we do. We used to have landline phones. Now it's just secluded to a mobile phone, which you usually carry everywhere. So yeah, research to power electronics can even make possible an inverter which we use in our home, which we use in a whole light our home, to just a compactable, pocketable form. We can do it after a lot of researches in the power electronics. So yeah, power electronics is very important. Even if power density increase is not large, that is a disadvantage. Sorry, that wasn't clear, I guess. The power density increase is not very large. That is a very disadvantage of a power electronic device. The gallium nitride, silicon carbon researches are being done, which will help us reduce 1/4 the size of the inverters we are being used. Microgrid, smart grid, etc. For all these concepts, without power electronics, it's not possible. That's why it has a very large possibility. So, I would like to conclude my session. I hope it was clear to everyone. My name is Devika Muraleedharan. You can contact me in this. Thank you. So, any doubts? I guess it was clear to everyone. Can we conclude the session now? So I guess no one has any doubts. So I'm concluding my session. Thank you.